best friend in the whole wide world because it does the simplifying of radicals and it does all those roots right away for you. So you don't have to do that on your own. Because if it doesn't say round to the nearest 10th or round to the nearest 100, then it means it's always going to be in what we call simplified radical form. And honestly, the reason why we do that, especially with the Pythagorean theorem and the next section that we do with what are called special right triangles, is that when you guys get into Algebra 2, when you get to the idea of what's called the unit circle, everything is built off of two triangles and the ratios of their sides. And if you understand how those two sides work with their square roots and stuff that are thrown into it, it makes Algebra 2 so much more easy, much easier. I'm very good at speaking, in case you didn't know that. So let's just kind of review this real quick. Like I said, for the most part, I bet you guys were like, oh, that's Pythagorean theorem, very cool. So let's see. Yeah, Josh, what's up? Sure. I just wanted to review this real quick about what these parts were, but I'll get to it because I'm going to build off of some of those things in there because I know that they had a couple things in there with some areas that you probably haven't remembered on some of those formulas, which is cool because what happens a lot of times when we get to a lot of the area stuff, as we build into those sections, I'm never going to have you memorize area formulas because that's but what I'll have you do is I'll have the formulas out. You just have to know how to use them. So if you happen to be one that was an area formula and you forgot one of them, don't worry about it. It's not a big deal. It's not the end of the world. But remember, when you're dealing with the Pythagorean theorem, really it's just a matter of can you identify the parts? Which part will always be the C value? The hypotenuse, okay. And that's kind of the main thing here, just to remind ourselves. The hypotenuse is always going to be the one that's across from the right angle. It is always, we don't say across from a lot of times, we're going to say the word opposite. The opposite, the right angle, will always be a hypotenuse. And then that makes these guys what are called legs. And it does not matter which leg is which. And sometimes they're the same. Sometimes they're not. Sometimes one of them's twice as large as the other, and so on and so on and so on. So what we have here then is just A, B, C. The Pythagorean theorem, believe it or not, is just the distance formula. Because I remember how we did distance formula before? Remember how when we had distance formula and I said, hey, there's an easier way to do this? Don't write this out, but remember when we did something like this and we wanted to figure out how far apart they were? We had that huge long formula, change in value of x quantity squared plus the change in values of y quantity squared, and we took the square root of it. Remember I said let's just count? We went 1 little 2 little 3, we went up 3, then we went 1 little 2 little 3 little spots, 4 little 5. Because that made a right triangle. And we did 3 squared plus 5 squared. That's where that comes from. That's where all this comes from. You never got the song. That's right, you never heard the song. Guys, we gotta help. She's new. She didn't know the song. Let's do that again. You don't know the song? All right. Let's do the song. All right. So we're gonna sing because we count spots. Ready? We're gonna go. Ready? 1 little 2 little 3. Come on. Let's go. 1 little 2 little 3 little spots. 4 little 5. Then you stop. We go that way. Ready? 1 little 2 little 3 little spot. Come on now. 1, 2, 3 little spots. 4 little 5 little 6. I'll stop. So you went up 5, you went over 6. You did Pythagorean theorem. I'm an idiot. It's okay. It's all right. It's quite all right. But that's where that comes from. The Pythagorean theorem is the distance formula, but you just never realized that's what you were doing all along. Or you might have. It's like, you're like, man, it's too early for this. So when you're going through problems, and hopefully we did some of these like this yesterday, a lot of times what we're doing, whenever I see, especially for the first few days of Pythagorean theorem stuff, whenever I draw my diagram, I'm always going to sit there real quick and I'm just going to identify I always identify where my C value is. I always label where your hypotenuse is, because that is the one thing that never changes. If you know where your hypotenuse is, then the other parts just fall in place. But it's a matter of always identifying that, because if you identify that, then everything else happens. Okay. The other ones, then it's just your A and B, and it does not matter which is which. So I know by now, we all know that's A squared plus B squared is C squared. It's just a matter of filling in the blanks. 9 squared plus X squared is 15 squared. And just pressing buttons on the calculator. Okay. Excuse me. Let's see, we get 81. Okay. Normally, when I take a square root over an equal sign, what do I have to put?
Plus or minus.
Very good. Because remember, the square root means what are two numbers that are exactly the same number that gives you something. Well, negative 12 times negative 12 is also positive 124. But you have to remember that in this case here, I can't have that negative distance value. So that's why we disregard the idea of a negative in this problem. So, like Josh said, it's 12. It's not that this is difficult, because I know that each and every single one of you have done this. Okay. Am I right in that? Now, as it gets into there, this one's another one. Where's your hypotenuse?
17.
So we have 8 squared. Notice the triangles.
Do you guys remember the biggest side is across the biggest table? You guys know that from last semester? And then the right triangle, and you got a 90 table, that 90 table is your biggest table. That's why the hypotenuse will always be the biggest.
So again, you get 64 x squared. What is that? 289? Is that right? You get x squared is 225. Square root it, and you get 15. Good morning, Mr. Smith. You're going to Washington.
I got my problem down.
No, listen.
10 minutes off.
What are you going to do? Oh, the bank's got all the not having money. Your money will save. It's been a long couple days. Once again, not crazy, right? Pythagorean theorem is probably one of the most useful things that you guys will use throughout high school. You guys had this stuff going yesterday, though. And, let's see. Yeah, well, Josh was asking about that earlier, right before you walked in, with the area stuff. I told him that no matter what, they'll always have area formulas, so they don't have to try to look that up. And I forgot that one was on there. Okay, thank you. So if going from there, it's not like they couldn't have figured it out. They could have Googled it. I don't know, right? So the weird one that gets thrown in here, and I want to show you guys what to do about number 11. Okay. Now, this is the type that you have to be very careful with your calculator. So at number 11 here, on number 11, that we say that as 8 root 2. That is playing the role of the hypotenuse. Good. So that's playing the role of hypotenuse. So you wind up with x squared plus x squared equals 8 root 2 quantity squared. And that's the trick. Anytime you've got a number in front of a radical, when you go to square it, you have to put it in parentheses. Because the calculator won't do it correctly unless it does have parentheses. Because this tells me, remember, junk squared means junk times junk. So this is equivalent to saying 8 root 2 times 8 root 2. What's 8 times 8? 64. Square root of 2 times the square root of 2 is square root. All right. Reminder, square root of junk times the square root of junk is just junk. Okay. Square root of junk times the square root of junk always equals junk. Read. Is any number.
So you do like, how about the square root of 25? And then you get square root of 25 squared is 25.
Another way to look at it, and you'll see more of this next year in Algebra 2. The reason why we multiply square roots together is because what are called exponent rules. You guys have dealt with a very small amount of exponent rules before. The square root of 2 is technically 2 to the half power. Okay? Because when you start going through, if you've done this before, if you have x cubed times x to the 4th, well, how many x's are here? Remember, x, when you cube something, it means it's times it, times it, times it. So you have 3 x's, and how many are there? 4 of them, which gives you how many x's? 7. So what happens here, whenever you have what's called the same base, the base in this case is what we call the variable x. When you have the same base with different exponents and you're multiplying together, all you do is add your exponents.
I like to call it the mod rule.
That's good.
And then when you divide, you actually subtract. And so I just remember you don't ditch your mod. Right? You divide, you basically say subtract that exponent. Multiply and basically
I like to say play war, because then that way you don't worry about negative exponents. Because if you've got a 7 and a 4, who wins? 7 minus 4. Or if it's 13 and a 5, who wins? 13. And he's not wearing a flotation device. So the same idea when you're talking about the exponent rules. A square root is a half power. So if you add 2 halves together, what do you get? A whole. And that's why that works. So this is a whole roundabout way that's saying that this is going to equal 64 times 2, which is 128. Now, in your calculator, you have to be careful if you don't type it correctly. If you type it in as 8 root 2 squared, if you type it in like that, it's going to just square root 2, and you're going to get 16. Whereas if you put parentheses around it, and this is a huge common problem, guys, you've got to remember. So I'm about to type 8 of this parentheses. 8. It'll happen to at least 2 or 3 of you throughout the course of this chapter. Absolutely. That is one of the most commonly thrown things on multiple choice stuff because that is the easiest mistake to make. So you will see that over and over and over. So back to this problem. 2 things going for you on this one. You have to be, first of all, you have to be very, very cautious with the 8 root 2 thing. You have to be very cautious with that, which gives you, what did we say, it was 128? Now, x squared plus x squared is how much? It's 2x squared. the same idea as x plus x is 2x. You're still combining like terms the same way. Now you have to think about how do you solve equations via working backwards. So you're not doing your PEMDAS. You are doing your SAD method. So when you're solving your equations, you're working your way backwards. So this is another one of those huge things that people do right now. They'll take the square root. If you go backwards via the order of operations, it tells you to undo subtraction, undo addition, undo division or multiplication, undo exponents, and then undo parentheses. So in this case here, I have to first undo the multiplication because that's the first thing that shows up before I get to the exponent. So how do you undo multiplying by 2? And this is why I wanted to make sure you guys saw all this. And now you're going to get a cleaner square root. Square root of 64 is. So in this case, that right triangle was formed out of a square, which makes, more importantly, what kind of a right triangle is that inside there? What is that called when you have two sides that are the same? Isosceles, very good. What do the base angles measure in an isosceles right triangle? If you have a 90-degree angle and it's isosceles, that means these two have to be the same, correct? Well, how many degrees are left? You already took out 90. 90. So what's half of 90? 45. That 45, what's called, this triangle here is actually what we call a special right triangle. It's called a 45, 45, 90 right triangle. And these guys have special ratios of sides. Something, something, something times the square root of 2. Which makes it also one of the basis of right triangle trig. Because all of these values are on what we call the unit oval. Actually, unit circle. 45 degrees is one of the building blocks of all trigonometry because of this special ratios that show up. It's not what we're looking at today. We'll probably get to a little bit of it maybe tomorrow. More than likely starting some of that on Thursday. Okay? We actually will spend a good chunk of time on that. That's right. Maybe we won't do it this week. Maybe start with it Monday. In past years, we've spent just on those two triangles, it's about a week. You know, solve that algebra problem. Does that help on number 11? I know that was going to be one of them that I figured people would have issues with. Yes, sir. Oh, well, good. Glad you didn't do it. Now you understand how to do it. Josh, you were talking about number 30, I believe. So go back through. 30 gives you have a couple of different ideas of how to. Do you know what shape that is? Good. More specifically. The trapezoid. Okay. Now, the reason those are parallel is because they're both perpendicular. That one is perpendicular to two lines. And the only way that can happen is if two lines themselves are parallel. Now, there's one of two things you can do. You could have looked up trapezoid formula or made this into a rectangle and a triangle. And that's what I would have done, because I forgot what the trapezoid formula is. But I know what a rectangle is. Rectangle is what times what? Good job. It's base times height. And to that, you'd have to add the area of a triangle, which is a 1/2 base times height. Now, when you're talking about bases and heights, it's generally where you look at your side lengths that create the right angles. So you know that this is 14 by 11. So your base and the height here is 14 by 11. Now, if this much is 11, how much is it for here? 9. And this is 14, so this just moves over to be 14. So it's 1/2. Oops. 14 by 9. A lot of times when you look at shapes, more often than not in our class, they're going to be composites of things that are very clean. They might be pretty easy to work with, especially if you forgot the formula for the upper one. Then it's just a matter of pressing a bunch of buttons on the calculator. But if you did happen to look up the trapezoid formula, I believe it is 1/2 the height times the sum of the bases. And those bases are the parts that are parallel. So you get the same answer going either way. So if you looked it up, it was 1/2 of 14 times 20 plus 11. And you'll get the same exact answer either way. Does that make sense on that? What else were you guys a little confuzzled through on that one? Yes, ma'am. Oh, I like this one. This one sets up almost a quadratic, and that's why it's a little tricky if you're not careful. Airline flies to 3 cities whose locations from the vertices of a right triangle. Total flight distance from A to B to C and back to A. Excuse me. So the perimeter of it is 1,400 miles. Okay. From B to A is 600. So if the total perimeter is 1,400 and you go 600, how much is left between from the other two sides? 800. Good. So we know that we have left here between for this section and this section, which is that's fine. I'm sorry, I hope we weren't cold. So there's 800 miles left. We don't know how much is in either one of them, but what we can do is this. If I call this much x, how much of it is left then for that one? If I call that x, I don't know how much I went. Remember this when I've said this before? From here to the door is 10 feet. I go 3, how much is left? 7. So from here to the door is 400 miles, or excuse me, 800 miles. Exactly. Now, you still have a right triangle. Which of those 3 sides then is hypotenuse? 600. Good. So you wind up with a quadratic. You get x squared plus the quantity 800 minus x quantity squared equals 600 squared. Now, when you have a quadratic, when you have what's called a binomial squared, that means it's junk squared. That means it's junk times junk. And you have to FOIL this. Okay, remember that? FOILing? In about a year. You do your first, outside, inside, last, or first, outside, inside. And it's really binomial. You guys ever see Billy before? That's Billy binomial. He's squid just right. See? Anyway, so 800 times 800 is what? 64, and then 4 zeros? Minus 800x, minus 800x. Negative x times negative x is positive x squared. And then we have an x squared here. No, because that's negative 800 minus 800. So you took a negative, you went more negative. So it would be negative 1600. So over here, I have 36. 1, 2, 3, 4. I believe that's 4 zeros. Start combining stuff. And this is where it gets a little messy. You get 2x squared minus 1600x plus 64. 2, 3, 4 is 36. 1, 2, 3, 4. And I know we did a couple of quadratic ones towards the end of last week with some of the similar triangles. All we have to worry about with this one is set aside equal to 0. So I'll subtract 36,000. And then we have a GCF. 8, 20, oops. Those guys are all divisible by 2. It's just kind of ugly looking. Ugh. And then going out of that. I don't use big numbers like this. Yeah, this is just awful because of the big numbers. The scenario of it isn't terrible, but if it was like 4s and 5s, yeah. And that's what sucks about this one. Because now you have to try to figure out what times what's 14,000 that you get, or 140,000 add together, you get 800. Let's see, so 7, 2. I screw something up there. 64 minus 20. 64 minus 36 is 28, right? Yeah. All right. It's just an awful digits. That's what you're looking into. Right. And Jai, you're right. Am I going to give you one with these god-awful numbers? Nope. Would it be something where it could have been, if this is 6, and this is an 8 minus x, could you go through something like that? It just makes the number smaller. And that's kind of what, and that's what I wouldn't make, this is awful, but that's the scenario. Could you set it up? That might be something I would do. Can you set up the Pythagorean theorem without solving? Is that fair? Because you're right, this gets to be really awful. The other thing that was thrown in there, and let's see, on the front one, we didn't get to the triple stuff yesterday on this, but what I wanted, what is that one here? The one thing that the Pythagorean theorem does allow you to do, I think I'm going to save triples for tomorrow. But one thing that you can do with the Pythagorean theorem that the textbook doesn't have, which what we're going to wind up doing more of today, is this. We know that if a squared plus b squared equals c squared, what kind of a triangle is that? It's a right triangle. So if this, you get a right triangle. You can do this also. You get all these different little scenarios that can occur. What I mean by that is the Pythagorean theorem and what's called its converse. I'll say things in reverse. You can use it on other things. For example, this is saying that this value, the hypotenuse is bigger, or that's longer than the other two sides. This is saying that it's smaller. All right. So if something's bigger, and you're thinking about types of triangles, you're thinking that's obtuse or acute. And that's kind of where you get it. What they do, though, is this. Textbooks generally write these backwards. the reason is because of how you say it. Because if I say if the c squared is larger than a squared plus b squared, it's obtuse. If c squared is smaller than a squared plus b squared, it's acute. Instead of saying if a squared plus b squared is smaller than c squared, then it's obtuse. See how it's like backwards from what you want to think, because you say smaller, but yet it's a bigger angle. So that's why a lot of textbooks will write it with the c values first. Remember, it's the same thing. Because with what's called an inequality, if 5 is less than 8, if I say that backwards, what do you get? Still a true statement, isn't it? Yeah. And that's the idea. You can say inequalities forward and backwards, and they're still true. So a lot of times you'll see them with that c squared first. So if that side happens to be larger than the other two, and it didn't create a right triangle, then you have an obtuse triangle. Here you have a acute. And for being as corny and silly as I say a lot of times, it's acute because it's lit up. I'm sorry. Really not. Okay, I get it. Not terrible, is it? Yes, ma'am. No, I did not. I can do that real quick if you'd like. This is really basically all I wanted to look at today because I don't want to get too crazy. There's only a few couple of questions here that I wanted to show you, but I can go to that one real quick if you'd like. Sorry, guys, I'm going to backtrack here real quick. When you're taking square roots with radicals in it, you're doing it the same way as you would for parentheses. So when you work with one like this, are you solving for a leg or a hypotenuse? You're solving for a leg. So it doesn't matter if I can put it first or second. I can say, so if I say this is x squared plus square root of 7 squared equals the square root of 19 squared. You had just come in right as we finished talking about square root of jump squared. What that means is square root of 7 times the square root of 7. Well, anytime you square jump, you get jump. So the square root of 7 times the square root of 7 is just 7. Okay? The square root of 19 squared would then equal 19. Subtract the 7 over, you get x squared equals 12. When you take the square root of that, then you get 2 root 3, and that is your exact answer. All right. Does that clear that one out? Make sure you put parentheses around stuff, especially when you get to ones that have a number in front of the root, like this 2 root 3. You don't put parentheses around it, you group it, you'll get a square root. Now, what I want to show you here, let me see if I can pull this up. Is I want to tell whether or not these guys are right, acute, or obtuse. So I want to check and see whether or not the side lengths of 5, 12, and 13 form a right triangle, acute triangle, or obtuse triangle. And using the idea that I was just showing you, that if we started by writing your c squareds first, c squared equals a squared plus b squared, it's a right triangle. If c squared is larger than a squared plus b squared, it is obtuse. If c squared is smaller than a squared plus b squared, then it is acute. So really, all you have to be able to determine which of those 3 side lengths is the longest, 5, 12, or 13. So you're checking. Is 13 squared in relationship to 5 squared plus 12 squared? So what kind of triangle is it? Bless you. Third time's the charm. So since they equal each other, 13 squared is 169. 5 squared plus 12 squared is also 169. That means that those three side lengths create a right triangle. That's what you're looking at doing. Same thing with 15, 36, and 39. Which one of those has to be playing the role of a hypotenuse, if in case it was? The 39. So you do the same thing. Notice I'm putting this little box in here. What's the relationship? That's what that means. Try it again. 39 squared relationship to 15 squared, 36 squared. I can't do that one in my head. I know it ends in a 1. As it ended in a 1, that's close. So 1521. And I do 15 squared plus 36 squared. Same numbers, right? Triangle again. Anybody notice the relationship between 5, 12, 13, 15, 36, 39? Look at the numbers. I'll do this by 3, but look at the relationship between 5 and 13, 12 and 36. There's a scale factor there, don't they? You're on the, yeah, this is 15, 36, 39 is 3 times the side lengths of those. So we knew that this one formed a right triangle, so if you did 5 times 3, 12 times 3, 13 times 3, you still get a right triangle. What do you think would happen if I took 5, 12, 13 and multiplied it by 5? It'd still be a right triangle. Because that scale factor stays consistent. That happens a lot. This thing, and we'll talk about this more tomorrow, this thing here, these numbers of 5, 12, 13, those happen to be what's called a family of triples. Family of triples are, there's about 4 or 5 of them that we look at pretty regularly, that if you take any scalar and multiply it to the family, you will always get a right triangle. 5, 12, 13. If I double it, I get 10, 24, 26. Those would equal a right triangle. If I triple it, 15, 36, 39. If I multiply them by 10, 50, 120, 130, those would also be a family of triples. Same thing goes for what's called a 3, 4, 5. What's 3 squared?
9.
What's 4 squared?
16.
What's 9 and 16? 25, which happens to be 5 squared. So those are these what are called family of triples that if you recognize patterns and you see those embedded in there like that, it just happens to make math so much faster. It's not that you won't have calculators or anything like that. It's the idea that if you can recognize special cases, special patterns, it makes it quicker. Plus, those are the type of things they throw in ACTs, SATs, because it's a time test. They try to see if you can pick up on those. We'll talk about that tomorrow. But take a second and do these 4 real quick, and I think we might just be able to call it a day. Tell me, are these right, acute, or obtuse? Please and thank you. The multi-view, if you type in the square root of 8 and you hit enter, it's going to say 2 root 2. Well, that doesn't help you with anything, but I need to know the decimal equivalent. You want to make a decimal equivalent out of that? Hit the double arrow button. What do you get? So is it bigger than 6, so we have to worry about it? No. That's the idea, because a lot of times these numbers aren't going to be written in largest to smallest or smallest to greatest. They're just going to be randomly thrown out there. So if you get something that says like the square root of 30, you don't know what the relationship is that to like a 16 or a 5. You'd have to type in to get the decimal equivalent to see where you place it in the generic setups. Okay. So if I'm checking this, then if we do the square root of 8 quantity squared, move this to the other side here. 4 squared plus that. What's the relationship to the 6 squared? Well, that's 36, 16, and 8. So 36 is then larger than that. So what kind of triangle does that make? Just write this down. Same thing with the root of 13. Is 12 squared, 10 squared, and the square root of 13 squared. Well, that's 144 and 113. So is it bigger or smaller? So it is obtuse. Okay. $28 squared. Something ends in a 4. 784. Thank you. This is 400, and that's a little bit more than that. Thank you. So that means this is smaller, so then that would be not terrible, is it? All we're adding into for tonight then is some of these style problems. Okay. The problems will be out of the book. I just brought my whoops. So you can add to the worksheet. Now let's collect the worksheet with this. Now we'll just staple them together in case you did it on a separate sheet of paper. So it's on page 496. I'd like you guys to go through numbers 16 through 32. They're real quick. They're real fast. Those shouldn't take more than 20 minutes. Okay. The only other thing that we have in this section is the triples. And we'll work on solely triples tomorrow. Okay. And then that'll get us to Thursday, and we'll be able to do maybe we'll do a little bit of construction on Thursday with some of these right triangle things we can make. Okay. We'll go from there. Dude.